Hello everyone, and welcome back to the C Programming with Windows API series. In the previous tutorial, we talked about advanced pointers and the concept of modifying or indexing and dereferencing an existing pointer variable. We also talked about type defs and type conversions, other known as typecasting. In this tutorial, we're going to be covering memory management and different topics which revolve around it. Let's go ahead and open up our Visual Studio IDE. So here I have the Visual Studio's IDE open up, as well as the topics which we're going to be covering under memory management. So we're going to start by discussing the difference between static and dynamic memory. So let's begin by talking about static memory. What is static memory? So static memory is memory that's been allocated specifically at the execution time. So it's memory that's been allocated by the programmer. However, it's memory that cannot change at any given time. It only takes the form of how many ever bytes were set to it specifically at the beginning of its initialization. So let's assume a char data type variable A as an array of 5 bytes. Right now, we've typically or basically statically allocated or statically set a variable A with 5 bytes inside of it, or it can store up to 5 bytes, but it can't store any more than this. Okay, so this right here is static memory. Now let's talk about dynamic memory as we move on towards the other topics of this tutorial. So I'm going to go ahead and I'm going to define a pchar, char pointer, and I'm going to set A as the variable equal to 0. Right now, I specifically initialized an array, a pointer A, setting it equal to 0. Now, for this course of this tutorial, let's take two phrases into account. Let's take these phrases. WinAPI is the best, and simply WinAPI. Okay? So these are the two phrases that we're going to be working with throughout the course of this tutorial. And I'm going to show you how you can allocate a specific set of memory, starting from this one, and then move into reallocating the memory into this phrase. So this phrase right here is 1, 2, 3, 4, 5, 6 bytes. Okay, so let's assume, let's assume that I take an array, a char array, set it equal to A of 6 bytes. If I'm to do this, okay, indeed, I can store WinAPI inside of this array. However, if I choose to add more bytes into this array afterwards, remember from like tutorial number 6 where we talked about arrays, we're going to encounter something called a status stack buffer overrun, meaning that this static memory cannot control the amount of bytes that we're going to be setting it into after. So we need to do something called dynamic allocation. So with dynamic allocation, I'm going to initialize a pchar char pointer variable A. I'm going to set A equal to a char pointer type conversion. And the reason I'm doing this is because what follows is a new function which we're going to be learning about right now called local alloc. Right here. Local alloc is a function from the Windows API which allocates the specified number of bytes from the heap, and the heap being the large block of memory during execution time that we have available to us. So we're going to allocate a specific set of memory from the heap. We're going to call local alloc, and local alloc being an hlocal type, which is a type definition for the void pointer. We can actually safely typecast this void pointer, whatever the return value of this being the amount of memory which we're going to allocate into A, we can safely typecast it as a char pointer. Because we can't specifically set a void pointer to a char pointer, however, we can allocate the void pointer as a char pointer, typecast it, and then set it. So the first parameter that local alloc expects is a flag. And the flag is the type of allocation which we're going to be doing. Okay? So let's go ahead and pull up the local alloc function reference sheet from the MSDN Dev Center. And we can see here that the parameters uFlag, being the first parameter, can be any of these flags here. And the flags are basically just preprocessor directives or definitions with these naming conventions, which actually point to these values. And these values perform a different operation depending on the value that's been passed inside the local alloc function. So for the case of this example, we're going to be using the lpointer flag, which as you can see is a combination of lmem fixed and lmem 0 init. The lmem part of this naming convention stands for local memory. Because we're dealing with a local alloc call, that's the naming convention that the Microsoft programmers decided to use, since it's very convenient. Take note, in local alloc, however, there is another type of alloc which we can conduct called, hold on a second, if we scroll down to the remarks section, we have this sentence right here, which says, Windows Memory Management does not provide a separate local heap and global heap. So basically, as we know, there's local variables and there's global variables. This sentence right here is saying that, yes, okay, so if there's a local alloc, there must be something called a global alloc, right? Because we have global variables and local variables. But however, in the reference sheet, it says that they don't actually provide a separate heap, so a separate source of memory where we can allocate from. Therefore, the local alloc call and the global alloc call or function are essentially the same, and they do the same thing. So they still allocate the same kind of memory. Again, they're just used as naming conventions, which you can assume that for local variables, we'll be using local alloc calls, and for global variables, we'll be using global alloc calls. So again, I'm just going to pass the lpointer preprocessor definition, which if we scroll over, we'll see it's a combination of lmem fixed and lmem 0 init. Lmem fixed being it sets this memory to a static point, a static amount of bytes, and lmem 0 init means that each of those bytes have a 0 set as the initial byte for that for this memory until we set it to something else ourselves. So I'm going to set this memory as a size of 6 bytes. And the reason I'm setting it as a size of 6 bytes is because Windows API is 6 characters long. And we also have to assume a +1, because remember how when we talked about arrays in tutorial number 6, we talked about how the array automatically gets a null terminator appended to the end of it? However, a pointer doesn't, and I said that a pointer only gets a null terminator appended to it unless we do so ourselves. And I said that I'll be talking about that later on being in this tutorial right now. So let's move on. Now I want to copy or set the variable a equal to WinAPI. And I can do this via a call known as copy memory. And I'm going to go ahead and pull up the MSDN reference sheet for copy memory right here for you guys. So here it is. So this is the copy memory function. And basically what the copy memory function does for us is it allows us to manipulate 2 separate pointers, a p-void pointer, or rather a void pointer and a constant void pointer. So it allows us to copy the block of memory from one location to another. The first location being the source, it allows us to copy memory from the source into the destination buffer. So in our case, the source buffer, or the source data type or variable will be WinAPI, and the destination will be A. So I'm going to go ahead and do that, called copy memory, and the destination, which is A, the source being the WinAPI string, okay, and the length being the length of the WinAPI string, which in our case is just 6, okay? So as you can see, this is actually a define or preprocessor directive for another call called RTL copy memory. And again, RTL copy memory is also just the naming convention for another call, which is, I know this is getting like call into call, but basically it's a preprocessor directive for the call memcopy. And basically, the only reason that copy memory exists is because it was an easier way for them to do than RTL copy memory, because RTL copy memory assumes that this is an RTL call, which RTL call is a part of the Windows API that has to do with the NT API, which is something we'll cover later on, but basically it's just a naming convention for 2 different frameworks of APIs within the Windows API framework. So the actual RTL copy memory call, by the way, points to a function called memcopy, and that's the actual function where action takes place. As you can see here, it's defined like so. It's just a more like English-friendly way of saying memcopy. Just copy memory. Copy memory B, which is the Win API, into A, which is, well, this allocated memory region here, of 6 bytes. And after we've copied the memory, something that we should do is set the null terminator. And how we can do this is we can simply call A, the pointer A, and define it as an array, because remember, we can reference pointers as arrays as well, assuming that we've allocated a size to it, like we have so now. We can assume that 6 equals to 0, and 0 is the same thing as the backslash or escape string 0, which is the null terminator string. We can also do it like this, or we can just set it to 0. And that null terminates the Windows Win API memory, which is now inside A. And the reason it's 6 is because you can imagine it like this: a char data type of the variable b as a pointer of 6 bytes equal to Win API. Or sorry, a pointer. I'm saying it's an array of 6 bytes equal to Win API, and oh, right, sorry. So for my example, I'm going to use 6. But the reason I'm using 6 is because I'm talking with this in reference to the pointer. So the reason I'm initializing the 6th character as a null terminator is because in an array, if you initialize this as 7, the 6th character here is assumed to be the null terminator, because remember, in computers, they start counting from 0. So this is 0, 1, 2, 3, 4, 5. This is the 5th character. And the 6th character being the character after this one, which in our case is 6 for our pointer here, we're going to be setting it equal to 0, because the pointer doesn't do it itself. And then all we're going to be doing is we're going to set a breakpoint right here. And we're just going to do a printf. Or actually, another unique thing, we're going to call a function called output debug string, which is just going to output a debug string, being like a string of characters inside our debug window, which we can use to examine what A is after we've allocated it and copied memory into it. So I'm going to unset this breakpoint and just change this to a release build and run the application. Just click any key to continue. Oops. Set it back to debug. Set a breakpoint here. Okay, so as we can see here, the A variable takes the form of Win API, which we've copied to it after allocating it. But take note, if we're just to take out this allocation and copy memory into A directly without actually allocating it before, doing the same thing without the allocation, this happens. Take note, we see the variable A is being used without being initialized. Even though it's a pointer and it points to a random index in memory, we actually have to initialize it before we're going to be setting some type of characters into it. Or it's going to give this error reading characters of string. You see 0xccccc, whatever. This value means that the variable has been uninitialized and it's not actually set to a specific number of bytes. So we must do the local alloc before, or just allocating it in general, before we're going to be setting some bytes into it. Okay, so now you're thinking, what is the difference between a char array? Like if I'm to set like a char array B of like 5 bytes, okay, and I just want to like take input from the user, like scanf, or rather printf, please enter a phrase, okay? And then scanf s b. Oops. So if I'm to run this application right now, I'm just going to comment, or a multi-line comment of this part of the code here, and then stop it there. If I'm to run this application here, enter a phrase to be stored inside this array. What if I'm to enter the Win API phrase? Okay, I get to my breakpoint here. Here, let me actually print it for you. Actually, afterwards. S B. Stop. Rerun. WinAPI. Okay, so the WinAPI phrase is actually outputted to the screen. However, we can't actually store the rest of these bytes in memory. So what I mean by this is, let's assume that I do something like this. Here, printf b. Yes. Set a breakpoint on this line. Run the application. Okay. Before doing anything else, I'm just going to add a watch on B. Oops. Just like highlight B. Add. Oh, I can't write because the console is asking me for input. I forgot. So enter a phrase. I'm going to do WinAPI is number 1. Okay. So notice how after I put WinAPI is number 1, it said like the value of B, whatever is inside B, is just WinApp. So the reason being is because it was only able to store 5 bytes inside of this array because we statically set the array to a size of 5. And when I outputted it, however, when I ran it, let me go back to the output. Sorry, this is from the here. I just closed it and now it's freezing. I'm going to stop the execution, remove this breakpoint, and run it again. Please enter a phrase, WinAPI is number 1. And see how it outputs WinAPI as number 1? The string can perfectly be outputted to the screen, to the user. However, being stored inside memory, as we saw when we set a breakpoint here and added the watch to B, let's rerun it again. Enter a phrase, WinAPI is number 1. We see that inside B, only WinApp is actually stored. However, everything else is stored outside of the current memory region, but when we actually output it, that context points to that memory region, so it's actually outputted as a whole string. But if we choose to manipulate this string afterwards, let's assume that we do something along the lines of, so after, let's say, copy memory B with an exclamation mark 1, and then ran the program. Enter phrase, WinAPI is the best. Okay. So here, I actually, +5, sorry. WinAPI, let's just do that. Okay, so the reason I just exited the program before is because I copied the exclamation mark to the first, because remember how I said in the previous tutorial when we talked about indexing the pointer, B plus 0, which if I just write B, it's assuming that I'm talking about the very first character of the B pointer. So that's why when I ran this application, I wasn't satisfied with the output because it printed inside the debugger output, it replaced the exclamation mark with the W of the WinAPI. So the reason I'm doing this is because I want to show you guys why we can't specifically set memory inside of a char array. This is why we use char pointers. So I'm going to run this like so. So I'm going to enter the phrase WinAPI. Now take note, I entered the phrase WinAPI. Here in the debugger, we don't actually see the exclamation mark anywhere inside the memory. Okay? So however, when we continue the execution of the program, so let me just do continue here. We have WinAPI being replaced with the 5th character. However, in the debugger, it didn't actually show the 5th character because the array is only set to store 5 bytes, and we can't actually see this exclamation mark in memory inside that array. However, if we're to do something along the lines of this, we set this, and then ask the user, please enter characters. Number of characters, and then we were to do a local alloc call on this B variable, then we can actually store as many characters as the user inputs, as many characters as we allocated into B. So then this would actually show, assuming that there's more than 5 characters allocated to B. However, with static memory, just setting it as an array of 5 bytes, we cannot do that. Oops. And yeah, so that basically wraps up the difference between static memory and dynamic memory. That also wraps up memory allocation. Now, an important thing to do after we've allocated a specific set of memory, and let's assume that like I print the memory printf a right here. So I printed it to the screen. An important thing to do after we're done using the memory, after we finish using the memory, is to free the memory. And the reason being is, there's two reasons actually. So firstly, it's so that we can reuse the memory after we're finished with it, in the case that like if we want to use the memory again in another point in our program, we can do so. And the previous contents will not be saved in that memory region. So how we can do this is we can just type a call or a function, Windows API, known as local free, and this frees the specified local memory object and invalidates the handle, basically sets the handle equal to 0. So we can call local free, and all it does is takes an hlocal bit of memory, in our case it's A, and it frees the memory A after we're done using it. So the second reason that we might want to do this, it's so that if we have a specific block of memory for like a critical operation in our application, and we want to keep adding contents to that memory, we want to free it every time, because in case it might go over its originally allocated size, something called a buffer overflow which will occur. And that's something that I'll actually talk about in the next tutorial, but we don't want a buffer overflow to occur because that'll crash our application. That's basically saying like if we have B set to 5 bytes and we're running our application at runtime, and we like just happen to store more than 5 bytes inside of B, the application will crash at runtime. Take note, at debug time it won't crash, but at runtime we put in release and actually run the exe, and it just so happens that more bytes are allocated to B than it can actually store, in this case 5, then the application will crash. So that's why we want to free the memory every time, and make sure that before copying the memory, we want to make sure that we can store that amount of bytes inside of the memory region of A in our case. So we do a local free just to free all the previous memory, and then we can continue on with our application to use that memory at any given point in time. So let me just run it, just so you guys can see that A will be freed after it hits this point. Okay, so A right now is, okay, so A is WinAPI right here, and after the A is freed, now A is nothing, and A just points to a random point in memory where it's just a random byte. Okay, so A is actually nothing, and it's freed, and now we can reuse A at any given time. Like now we can just do like another local alloc followed by the amount of bytes that we want to allocate into A. But now let's assume that we want to allocate, we don't want to free it yet, but let's assume that we want to add like is the best or space is the best onto this WinAPI string inside of A. We've already allocated or locally allocated 6 bytes plus 1 inside of the A variable. So if we want to store more characters inside of the pointer A, we can do something called reallocating the size of the array, or the size of the pointer in our case. So we do this by calling A, setting A, or rather, we're going to be doing this before we null terminate the string. So we're going to set A equal to a char pointer cast to the function local realloc. And let me actually pull it up for you guys here. So here we have the local realloc call. As you can see, it takes 3 parameters. The first parameter is the memory which we're going to be reallocating. The second parameter is the number of bytes that we're going to be allocating on top of the current amount of bytes. And the third parameter is the flags. So what this function does is it changes the size of the size or the attributes of a specified local memory object. The size can increase or the size can decrease if we want to just store less amount of bytes inside of the variable. But in our case, we want to store more, so we want to increase it. And how we do this is we open up the brackets. We can see here, let me just stop the execution. After opening up the brackets, the first parameter is the memory itself. So in this case, we're dealing with the A variable. The second parameter is the amount of bytes that we want to reallocate on top of the existing amount of bytes. So in our case, the existing amount of bytes is 6. So we write 6 here, plus how many bytes we want to store inside it. So in our case, we want to store 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we want to store 12 more bytes on top of WinAPI. So we simply add 6 plus 12. Plus, we have to add 1 because we're including the Null Terminator at the end. And the flags. So for the flags, we can actually set these following flags. So we can either set lmem movable, lmem 0 init, or lmem modify. But in this case, we're setting lmem movable because we want to set more bytes into the string. So we're kind of moving extra amount of bytes that we can set into the char pointer. So we're just going to call the lmem movable flag. Okay. And now we can do another copy memory A, and we're doing A plus 6 because this right here is 6 characters long, and we want to copy the string. This string space is the best after WinAPI, and this string is 12 characters long. Okay, so now let's just do a printf A right here. Oops, printf A. Okay, and then run the application. Sorry, let me just first stop it, put it in debug, and then rerun the application again just so you guys can actually see what happened. We can see that A contains WinAPI space is the best string now. After we've reallocated the memory and then copied is the best 6 characters after the beginning of the string, which is WinAPI. And after we're done using the memory, after we've printed it to the screen, we can simply call local free, saying that, okay, we finished using the memory, free the memory, and return the originally allocated memory back to the heap. So we'll run it. And now we can see WinAPI is the best, print it to the screen, press allocate to continue, okay, and that's it. So in this tutorial, we covered the difference between static and dynamic memory allocation, why it's important to free memory, and memory manipulation, which in this case was through our copy memory function. So that actually wraps up everything for this tutorial. Stay tuned while in the next tutorial I talk about heap overflow and stack corruption, as well as stack overflow or buffer overflows, which are specific errors that can occur during runtime execution of our program. And if you like this video or learned something new, please leave a thumbs up. If you have any questions, feel free to leave a comment down below. And stay tuned for the next tutorial. See ya.